All right, page number 3. We got a car starting at the 20 centimeter mark and it moves forward after 4 seconds. It's gone to the 60 centimeter mark. We want to write down its equation of motion. So here's the thing. Your temptation is to just go, oh, x is 20t plus 60, or x is 60t plus 20. And that approach is not going to work in physics. We actually have to think about what's going on with these numbers. So let's draw the little ruler here. And I absolutely reserve the right to throw questions like this on an exam. I make no apologies for stretching your thinking skills and putting things on exams that aren't completely what you see in class. So what we're saying is that a car starts here, and that in 4 seconds, it rolls to here and keeps going, but what we noticed is that it took 4 seconds to get there. So to get the speed, I'm just going to use the dirt equation. Distance is rate times time, which is just I travel 260 from 20, and that's going to equal r times t, and t is 4 seconds. So I'm going to end up getting a rate of 10 centimeters per second. Another way to get this is I could say x is v naught t plus x naught. So I have the general physics equation, and then what I want to do is figure out, well, can I actually get the speed from this? So I know I wind up at 60. I don't know my speed. It takes me 4 seconds to get there from a position of 20. And when I isolate v, I'll also get 10 centimeters per second. Either way works. So when I say write down its equation of motion, I want to be able to predict where it will be at all times. So that means here my equation is x is 10 times t starting off at 20. Okay. I expect you to be able to see that why there's an x and a t there are not more numbers, or why there isn't a number answer to this. We talked about this in the first video. If you're still not clear on this, we need to make some time to talk. So how far will it be after 8 seconds? X is 10 times 8 plus 20, and that means it's at 100 centimeters. It's at 100 centimeters. Now, when I want to plot its position as a function of time, let me just actually use all the graph paper. And I do expect you to do this. I do not want you using like 3 squares by 3 squares on these graphs. Okay, I provide all this space for a reason. Okay, so let's just do this. So we'll say 2, 4, 6, 8, 10, 12, 14. All right, cool. So 2 seconds. Say so 2, 4, 6, 8, 10, 12, 14, and this is the time, and it's in seconds. And then we also have position in centimeters, and I'll label this position versus time. Awesome. Now here, let's just count. So we'll say 10, 20, 30, 50, 60, 70. You know what? I don't like that. We're going to say this. We're going to say here, this is 20, 40, no, 20, 40, 60, 80, 100, 120, 140. Sorry to cramp it, but my pen tool doesn't work beyond that. So at 0 seconds, I'm at 10, and my position increases at 10 centimeters a second as I continue here. And let's make absolutely sure I have that right. Does it start at 10? No, it doesn't. It actually starts at 20 centimeters. And let's just double check something here. You notice that at 8 seconds, I'm at the 100 centimeter mark, just like my equation predicts. So it's a good way of knowing whether my graph is good or bad. And so I'll just actually draw a line through these dots. Okay. I did it this way. You need to use a ruler. I can't because I have this weird tablet that doesn't let me do that. So here, I'm going to draw a graph now of the velocity versus time, a different animal. So first thing I'm going to do is count off. And so I'm getting 2, 4, 6, 8, 10, 12, 14. This is the speed in centimeters per second. We got the time. So again, 2, 4, 6, 8, 10, 12, 14. Awesome. This is the time in seconds. And so when I actually plot this, I got that my speed was 10 centimeters per second. So I'm going to take a nice bold line and draw a flat 10 centimeters per second the whole way. That was my attempt at drawing a flat 10 centimeters per second. That's as close as we're going to get. So this, again, is a graph of velocity versus time. And so we've done the third problem.